Hi, Dylan.
Hey, Professor P, how are you?
Great. I'm doing fantastic. You have your good hurricane day?
I flooded quite a bit, but yeah.
That's right. I'm sorry. I forgot about that you had problems. Oh, I'm
No,
sorry
it's okay.
about that. You actually flooded, your house did?
Not my house. It almost got to my house, but it totaled two of our cars.
Where were they parked?
I live in Shore Acres, so right in my driveway.
You live in Shore Acres? Right by
Yep.
Driftwood?
I'm not sure.
Okay, by what's the park that's there? Lantana or something like that?
I'm not sure, honestly.
Do you get to your place by going 22nd Avenue South?
No, I live further up.
Okay.
By Venetian Isles.
Okay, I got you. I got you now. Never
Yeah.
mind. Never mind. I thought you were like within spitting distance of me. Apparently not, though. I see somebody else joined us. Joe.
Yeah.
Dr. Joe. Good, good, good. I got two of you here. All right. Joe, are you in the lab or not?
No, I have a different lab.
Good. Okay, that's fine. I'm just going to give you guys I was just going to say, I'm going to give you the opportunity to take the final from the 30th through the 2nd of December. That seems to me to be the fairest.
Thank you.
No problem, Dylan. I just work it around. I know that week's going to be packed with tests. Just work it around whatever tests you have. I know we're going to have a test in here probably on the 1st. I think it's scheduled for the 1st of December. Nope, 3rd. I've got it scheduled for the 3rd. All right. Well, there we go.
My birthday's the 5th.
I'm sorry?
My birthday's the 5th.
Congratulations. How many years, Joe?
20.
You got a long ways to go.
Yeah,
You're not even
good.
a third of my age yet, Joe.
It's
Even
big 2-0,
next
though.
year. I'm sorry. Go ahead.
It's the big 2-0, though.
Yeah. No, next one's a big one. My grandson is going to be 21 in April, and we have a time capsule for him that we put a whole bunch of stuff in this 5-gallon bucket way back when. And this year we're going to open. I also have a bottle of wine that was corked in the year 2000. So he's going to get a chance we're going to get a chance to open it and drink it, or not. My guess is it's vinegar by now, so who knows what's going to happen with it. Yeah, $150 later. What can I tell you?
Oh, no.
I bought it way back when. It's like, have you ever seen a Magnum, one of the big bottles of wine? I bought one of those for him, so we'll see what happens. Don't know if anybody else is going to join us, but let me ask you, how good are you at how solid do you feel doing Lewis dot structures? Do I need to review this at all?
I feel fine doing it.
Dylan?
I think I'm all right.
Okay. Then in that case, I'm going to go on further. I believe I ended at formal charge. Are you okay with that, or do I need to go over that a little bit?
No, I think I'm good with formal.
Yeah, same.
Okay. Good enough. I'm here to serve you guys. All right. That means we can get on with yeah. Stop doing that. Okay. Now, are you both going on to organic?
Yeah.
I'm not sure.
I am.
I forget.
Okay. If you're not going on to organic, this is going to be like a one and done type thing. In other words, you just have to get through it right now, and you're never going to have to worry about it again in your entire life. Now, there is such a thing as resonance. Resonance it means you are able to manipulate double and triple bonds within the molecule so that you can create a correct Lewis structure. I'll give you a perfect example here. Do you see how this is ozone? Do you see how it has one double bond and one single bond?
Yeah.
What makes the right one so special that it gets the double bond? Is there anything about that right oxygen that makes it super special that says, hey, I got to have that double bond? Anything special about that oxygen?
It's neutral.
No.
No, there's nothing special. Could I put that double bond over here?
Yeah.
Dylan?
Yeah.
I could put the double bond over here, take this lone pair, put it over here, and I'd have pretty much the same molecule, right?
Yeah.
All right. That's an example of my being able to manipulate double bonds within a chemical structure. And if I actually look at an ozone molecule, I actually will look and see the bond length between the left and the right oxygens. That bond length is the same. Now, if it were on one or the other oxygens permanently, what would happen is you'd have much more of an attraction of this oxygen for this one. There'd be much more of an attraction there. So this bond length would be smaller than the other, but it's not. They're both the same. So that means something is happening here. And I'm going to get into this a little bit later when we're talking about hybridization. But the way you make double bonds is you have p orbitals. You have unfilled p orbitals that are out here. And so you have a p orbital that's on this oxygen, and you have one that's on this one. So what happens is those p orbitals share their electrons. But looky, over here, I have another p orbital. It could also share its electrons. So what ends up happening is those electrons are spread out throughout the entire molecule. And when they're spread out throughout the entire molecule, it makes the molecule much more stable, much stronger. And the other thing is that is said to delocalize the electrons. In other words, the electrons are not over here, they're not over there, they're spread out throughout the entire molecule. So, and I'm going to stop screen sharing here for a second. So I have to have the ability of, stop calling, thank you. I have to have the ability to manipulate double and triple bonds. Okay, say I have this molecule. I have a carbon double bonded to another carbon, but to that second carbon, I have two H's. To this carbon, I have two H's. Now, the first thing you need for resonance is you need double bonds. This clearly has a double bond. But in this molecule, can I put that double bond any other place?
No.
Not really. I can't really put it any other place. Now, if I draw another one, now look at this guy. Can I make this any different? Can I manipulate a double into a triple bond, or can I move those double bonds anywhere else in this molecule?
Could you bind the hydrogen atoms to the other hydrogen atoms?
This way? No, because
Like move.
move this guy up here. Is that
No,
what you
take one from the other side and
Move-
attach it to it.
to move one here? Where am I going to put it? Over here?
No, that wouldn't work. Never mind.
Okay. I can't even do like triple bonds here because if I put a triple bond there and take this one away, that makes 10 electrons around this carbon and only 6 around this one. It's not going to work. So I don't have the ability when I have propane diene, when I have that compound, I don't have the ability to manipulate the double bonds. So there's no way that I can have resonance. On the other hand, if I have something like this, oops, sorry, that should be a C. Is this going to have resonance? I got a double bond between these two, right? Is there anything that says I can't put that double bond right there and move one of these hydrogens over here?
No.
So that means this has resonance and the electrons are all in here, okay? They're delocalized. Is that making sense to you?
Yeah.
All right. I believe I went through this yesterday or Tuesday of last week. Remember I said that we could draw this way? We could draw it that way, or we could draw it this way. Is this a legitimate drawing, Lewis drawing for carbon dioxide? Are both of these legitimate drawings?
Yeah.
This
'cause we both-
this one is much more favored than this one. Okay, this one, oh, let's undo that. I don't like it. This one, much more favored. It's the star. That's supposed to be an asterisk. I hate etch-a-sketching. So this one's a star, but it still exists to a little extent this way. As long as you can manipulate and create a legitimate Lewis dot structure, you have resonance. Make sense, guys?
Yeah.
Okay, I'm going to new share and go back to this guy. Do I have resonance in this thing?
Yeah, because you're just changing the double bond.
Okay, probably the most famous. I'm going to go back to the whiteboard. Stop share. Probably the most famous one. This is a compound called benzene. Everywhere where you see an angle, that's a carbon-carbon bond. Now that's benzene. Can I draw this any other way? Why does this double bond have to be here? Can that be shifted over here? Which means this one would shift over there, which means this one would shift over there. Are these equal structures?
Yeah.
Resonance. As a matter of fact, there's so much resonance in here that it's hard to break up. It's hard, this molecule is so stable that the body can't break it up. And it kind of like sticks around in the fat tissues until the body decides to react against it and create tumors. Benzene is a very big known carcinogen. Okay, so I'm going to stop talking for a second and I'm going to try and get a video up here. Don't know if it's going to work. Did this morning. It's my favorite video. 2 minutes out of your life. Okay, I'm going to pause it, stop. All right. Go over here. Share screen. Can you hear it? Can you hear it?
Haven't played it.
Can you hear it now?
No.
Okay.
Yeah, no.
That's why I asked the question. Now can you hear it?
Yeah.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
Sorry, isn't that brilliant?
Yes.
Dogs make everything better.
Your enthusiasm is underwhelming. Okay, so we have to talk about polar bonding, okay? When we have covalent bonding, as we've been discussing this whole last period when we've been doing Lewis dot structures, we're actually sharing electrons, okay? Sometimes, though, that sharing is unequal. So if I have a fluorine mixed with another fluorine, there's no difference between them. So the electrons are happy to spend equal time between each fluorine. On the other hand, if I have a hydrogen mixed with the fluorine is much more electronegative than the hydrogen. So the fluorine is going to want the electron to spend more time around it, less time around the hydrogen. So what we get is we get a molecule that has a negative end to it and a positive end. It's not always that way. It's kind of almost temporary because the electrons do go back to the other atom on occasion, but they spend so much time around the one ion that it can be looked at as having like a negative charge to it. And just to give you an idea back about electronegativity, electronegativity is nothing more than a relative scale that rates an atom's ability to attract an electron to itself. And fluorine is the most electronegative. In this case, cesium would be the least. As you go up a periodic table, the electronegativity increases. As you go from left to right, the electronegativity increases. So that when we have these kind of bonds, we literally have a positive end and a negative end to that particular bond. If I have a pure covalent bond, the electrons are spending the same amount of time around each atom. There's no charge on that. If I have an ionic bond, there's such an electronegativity difference that the one atom will steal the other atom's electrons. So can you see that these two things are kind of almost the same thing? They have charges that are involved in them. Since they have charges that are involved in them, they mix very, very well together. On the other one, this doesn't have charges. So it's going to kind of repel against these things that do have charges. So pure covalent bonds will be attracted to other pure covalent bonds. Polar covalent bonds will be, polar covalent and ionic will be attracted to polar covalent and ionic bonds. And if we're looking for, if you want a number sense of this, if the electronegativity difference is between 0 and 0.5, then what happens is the electronegativities are too close to one another. You're going to have equal sharing of the electrons. Between 0.5 and 2, you're going to have one of the atoms that's going to control the electrons more time, so it's going to be a polar bond. If you get higher than 2, that means that you've got a total stealing of the electrons from one to the other. Generally speaking, you indicate that by either using this small case delta. This actually is a small case Greek letter delta. You indicate what the positive end is and what the negative end is. Or the other way you can do it is just by having an arrow with the head pointing towards the negative end. Now, what this means basically is if I've got a positive end and a negative end to a molecule, and I put this into a magnetic field, I have a positive magnet up here, negative side there. What's going to happen is this molecule is going to rotate in that magnetic field so that the blue atom is on top and the red one is down below. Okay, we good with resonance and polarity. I'm going to get back into polar. When I talk about the VSEPR and I go into polarity of the entire molecule, I will bring polar bonds back again. I just needed to talk about that right now. Are we good about that in resonance? We have a fairly good feeling for those?
Yeah.
Yeah.
Okay. Now, unfortunately, I have to drag you kicking and screaming back into thermochemistry. All right. Breaking bonds is endothermic. You have to put energy into something to break chemical bonds. If, on the other hand, you create a bond, that's exothermic. So the energy associated with breaking bonds is positive. We got to put energy into the system to break the bonds. The energy that is consistent with forming bonds, if you form bonds, it makes a more stable arrangement. Energy is given up. So if I'm looking at an entire chemical reaction, my change in the heat of reaction is going to be equal to the sum of the bonds broken minus the sums of the bonds formed. All right. And you're going to have to wrap your heads around this because this is kind of counterintuitive to what we did before. What you will be given is you'll be given a chart. If you notice, all of these are positive. We've actually determined the bond enthalpy of the breaking of that bond, how much energy it takes to break the bond. Forming that bond, it's the same amount. It's just that the sign is going to be negative. So if I have a simple chemical equation, I have two H2s plus an O2 making two H2Os. I need to break. I have two molecules of hydrogen there. I need to break two HH bonds. And I need to break one O bond in order to make two H2Os. Now, Dylan, H2O, what bonds are in H2O?
Hydrogen and
What's a hydrogen bonded to?
the oxygen. Oh.
One hydrogen is bonded to the oxygen in a H2O, and the other hydrogen is bonded to the oxygen. So you have within each molecule of water, you have two OH bonds. If I make two molecules, this means I have to form four OH bonds to make this work. Are you kind of understanding what's going on here?
Yeah.
So if I want the enthalpy of this entire reaction, I got to add the breaking of the HH bonds. I look over to my chart and somewhere around here. So, oh yeah. An HH bond, to break an HH bond, it takes 436 kilojoules per mole. Okay. So I have two of those because I have two HH molecules. I have two of those bonds to break. So I have to multiply that by the amount it takes to break one bond. On the other hand, I only have one oxygen, and that's an OO bond. So I look at my chart. I find OO. To break that bond takes 146 kilojoules per mole. So one OO bond, I multiply that by 146. We said there were four OH bonds. An OH bond is 463 kilojoules per mole. So I'm going to multiply the four bonds by the amount it takes to form each bond. The amount it takes to form each bond is a negative number, or I'm subtracting the bonds formed. I have the 2 times 436 plus the 1 times 146 subtracted the 4 by 463. I have negative 834. But if I'm asking the heat of formation for 1 mole, how many moles of water did I form here?
2.
So this 834 is the amount of heat that's required, that gets given off to form 2 moles of water. To get 1, I have to take this 834 and divide it by 2.
Wouldn't you use the multiple bond number for O2?
The multiple bond. Where you see it?
Under multiple bonds, it's on the last column.
Ah, you caught me in an error. Very good, Dylan. So this is 1367. Minus 1852, 485. Divided by 2. And that's actually very close to what it is. Actually, I'm going to look that up. All right, sorry. What's that at? H2O. I've got H2O as a gas being negative 241. So that's very close to what the real answer should be. Questions on this? Now, at the risk of confusing you, when you were doing this, do you remember when you were doing it back in thermo? We would do the sum of the products minus the sum of the reactants. Do you remember that?
Yeah.
Okay, this seems counterintuitive, but you have to understand a couple of things. One of which is when we were doing sum of the products minus sum of the reactants, the heat of formations weren't always positive, were they?
No.
Or they weren't always negative. The chart I showed you, all these numbers are positive. So that's one of the reasons why. The other reason is we are doing specifically bond breaking and bond forming. Did I confuse you, or are you pretty much good yet?
I think I'm good.
Joe?
Yeah, it's just like the last thing, yeah.
Okay,
a
we
little
got
bit,
two
but-
more problems, then we're going to be done with this, all right? Okay, I have CH4 plus Cl2 making CH3Cl and HCl. Okay, what bonds were broken to do this?
CH4 and Cl2.
So you're saying, Dylan, that I broke all 4 CH bonds.
No, it
How
was
many
a
CH
Cl.
bonds did I break?
How many H bonds?
How many CH bonds did I break?
1.
1. Joe, do you see that?
Yeah, one.
If you're having trouble with this, draw out the compounds in Lewis dot fashion, and you'll be able to see it. There's one CH that gets bonded, and then a Cl gets put in there to replace it. So I have one CH bond broken. I also broke one ClCl. Now, what I formed was what? What did I form, Joe?
CH3Cl.
No, which particular bond? I broke a CH bond off of the CH4. So what did I do to make
Formed a
CH3Cl?
CCl bond?
CCl. So I formed a CCl bond. Okay? That left me with a hydrogen floating around and a chlorine floating around. They linked up and made HCl. So I formed another bond. The bond's broken. I have one ClCl. That was 242. One CH, 413. From that, I subtracted the CCl bond and the HCl bond. Does this make sense, guys?
Yeah.
Joe?
Yeah, I got it. It's the only first thing is like the only first part is confusing, but I understand a little bit.
Okay. Now, Joe, let's look at this, all right? I have CH4. What am I making from it?
CO2 and H2O.
CO2. Okay, and the H's are going. So in this instance, did I have to break all 4 CH bonds?
No.
Do you see any H's in here, Joe?
Oh, no.
So did I have to break all 4 of them?
Yeah.
So I had to break 4 of these to make the CO2. I also had to break the OO bond. And again, this is going to be a little screwed up. This should be 495. Okay. So I have 4 CH bonds positive, 1 OO bond positive, minus, if I look at the C double bond O, that's a triple bond, I believe. This one down here below is triple bond. The double bond O is 799, and the 4 OH bonds are 4 times 463. And I will figure that out presently. $21.47 minus $15.98. Negative 1303. Questions about this? This is probably going to be the only numerical problem you have on the next test. I would anticipate one of these problems, okay? I got a couple minutes. This is the interesting part of what we're doing. This is how you separate all the elements from one another. If you have all these ions up there, what happens is if you add HCl, the silver, the lead, and the mercury will all precipitate out. So everything else is left in solution. You'll have solid silver chloride, mercury chloride, and lead chloride. Remaining cations will be there. So what you do is you add the gas H2S and HCl. What that reacts with is this whole second band. Everything else is left in solution. To that you add ammonium sulfate. All of these precipitate out, remaining these guys. If you add ammonium, hydrogen phosphate, that will precipitate out these guys, leaving these. This is a flow chart on how to identify different ions. So if you want to identify whether you have silver, mercury, or lead, add HCl to it. You'll precipitate out something. That means you have one of those 3. It's probably longer than I should have been on it. Take it for what it was worth. That is the last slide in this presentation. Any questions on Lewis dot structures, resonance, formal charges, polarity, or bond energies?
I'm good.
Okay. We're going to stop share. And we're going to go from there to the other slideshow. And take it here. Valence shell electron pair repulsion, VSEPR. Okay, do either one of you have a little brother?
Yeah.
Good. Joe, were you
Hmm?
ever put in the car in the back seat with your little brother?
No, because I always sat in front.
You never sat in the back seat with your little brother.
Yeah, sometimes actually, yeah.
How long was it that you were in the back seat before one of you was saying, he's touching me? Dad, make him stop touching me.
All the time. I have 3 of them.
Okay. Same thing with electrons. Electrons don't like to be near each other, so they want to get as far away from the other electrons as they can. That is the whole basis behind VSEPR. So here, we're going to go through the VSEPR theory. We're going to talk about the bond angles that happen there. We're going to be talking about polar bonds and, more importantly, polarity of the molecules. Then we're going to get into something called hybridization. We're going to learn how to do hybrid orbital diagrams. I'm going to talk about sigma and pi bonds. Then we're going to get into molecular orbital theory. And in there, we'll talk about bonding and anti-bonding electrons, bond order, and being able to predict para and diamagnetism. Whole bunch of stuff in this chapter. So basically, the whole basis behind VSEPR is, as I was talking about, that you're touching me analogy. Electrons want to get as far apart from their brethren as possible. You minimize electron pair repulsions by getting them as far away from one another as you can. Now, I got to count them whether they are lone pairs or bonding. Lone pairs and bonding, they both repel each other. They want to get as far away from one another as is humanly possible. But by the same token, electron pairs occupy more space. Lone pairs occupy more space than the bonding electrons, because the bonding electrons are kind of confined to being between the atoms, whereas there's no real confinement for the lone pairs. By assuming that we want to put these things as far away from each other as possible, we can come up with a molecular and an electronic shape. But we need to have some vocabulary first. An electron cloud, you will see them described as electron domains. An electron cloud is any lone pair. If I have 2 lone pairs around the center atom, that counts as 2 electron clouds. 3 lone pairs, 3 electron clouds. Okay? If I have a single, double, or triple bond, each one of those counts as 1 electron cloud. And let me explain why. If I somehow had a double bond there, right? Wouldn't the electrons be located in the same area? All the electrons from the double bond as for the ones for the single bond? Wouldn't that be true?
Yeah.
So we're looking for locations now. So if the electrons are going to be in the same general place, then single bonds count as much as double, which count as much as triple bonds. So we're going to count the number of electron clouds that are around the center atom. Okay, we have to define a lone pair as any pair of electrons that's not involved in bonding. Those are the electrons that are controlled by the atom they're attached to. They're not controlled by any other atom. Bonding pairs are controlled by the atoms to which they bond. So if I have, in that last instance, the H bonded to the N, the bonding electrons are the ones which keep the H and the N together. All right, if I'm counting this single bond counts as 1 electron cloud. Double bond counts as 1. This single bond counts as one. This lone pair counts as one. I've got 4 electron domains. Are we good with that? We're good with that? Solid on that?
Yeah.
Joe?
Yeah.
Okay, there is something called an electron domain geometry. Electron domain geometry includes all of the electron clouds, including the lone pairs and the bonding. But when I'm dealing with a molecular structure, if I want a molecular geometry, I can't see the electrons by themselves. So all I can see are the atoms. So I have to account for the lone pairs making a general shape, but the only thing I can see are the actual atoms themselves. So if I have 4 things around the center atom, that makes a shape called a tetrahedron. But if one of the spots is occupied by a lone pair, I can't see it. The only thing I can see is this red atom and these 3 silver atoms coming off of it in an angular fashion, so that this looks like a triangle side, another triangle side, and one on the back end. So it looks like a triangular pyramid. I could take another one of these off, replace it by a lone pair. I can't see this portion of the molecule where the electrons are. All I can see is this silver atom bonded to the red one, bonded to the other silver. So I have a different shape for my molecular geometry than I do for my total electronic geometry. All you got to do is count the number of electron clouds. That will determine what your electron geometry is. If you have 2 electron clouds, these electron clouds want to get as far apart from each other as possible. What that creates is a 180-degree bond angle, and they're as far apart. We have a linear geometry. Now, if I put a third thing in there, let's see. If I put a third thing in there, what happens is this one other atom comes in, it starts to repel. It starts to repel. Now, this one is repelling this one and this one greater at first than these are repelling back, than these are repelling each other. Okay, let me redefine it. You see where the arrow is right now? Because the arrow, if I've got another atom coming in here, it's closer to this one and this one than these are to each other, correct? So this one pushes these guys down until they get equidistance apart. And so instead of a 180-degree bond angle, I now have 120 degrees. I shove another one in there. Now, if you remember back to your geometry, 3 points make a plane, correct? If you have 3 points, you can draw a plane through them. Am I correct in that?
Yeah.
I put a 4th thing in there. I have to evoke the 3rd dimension. I have to do the height portion of it. So if I'm approaching this atom with this molecule with another atom straight at that blue molecule, that blue atom, can you see that as I'm pushing that other atom towards the blue one, that new atom is pushing the other ones down, so that you have this one pushing this one down, and this one down until they get equidistance apart. That creates a shape known as a tetrahedron with a bond angle of 109.5. Now, if I shove something else in there, what happens is it pushes this one back and this one back until they're vertical. And then the three center ones have a 120-degree bond angle, but between the top one and the plane of the three and the bottom one and the plane of the three, there's a 90-degree angle. I shove another atom in there, I create all 90-degree angles. This is how VSEPR is working. So if I go back to my electron cloud geometry, if I have 3 electron clouds, I'm going to have a trigonal planar geometry for a tetrahedron. If I have 5 electron clouds, the electronic shape is going to be trigonal bipyramid. 6 electron clouds, it's going to be an octahedron. Now, when I'm dealing with molecular geometry, I don't account for the electrons. If I have water, the water molecule actually has a lone pair over here and another one over there, but I can't see them. All I'm seeing in the molecular geometry is the hydrogen to the oxygen to the hydrogen, which has a bent shape. When there are no lone pairs on the center atom, when there are no lone pairs on the center atom, molecular geometry and electron geometry are the same. If I put a lone pair on the center atom, the molecular geometry is going to differ from the electron geometry. So if I have 3 electron clouds, 1 lone pair, basically I take away this top atom and all I can see is this here, which has a bent geometry. If I have 4 domains, I have a tetrahedron, 1 lone pair. I take the top one away and the general shape of this looks like a 3-sided pyramid or a trigonal pyramid. I put 2 lone pairs in there. I get a bent molecule. If I have a trigonal bipyramid and I take 1 atom off, I have the molecular shape becomes a seesaw. And if you like to think of it, you see how this can act as the lever and this side can go up and down and this side can go up and down. That's how that's called a seesaw. 2 lone pairs. When I'm taking the atoms off a trigonal bipyramid, I'm taking them away from the planar, the trigonal planar portion of the shape. So I take a second one away, this becomes T-shaped. I take the third one away, all 3 atoms from the center plane have been removed, I have a linear molecule. Octahedron, if I have 1 away, what I have are 4 sides to a pyramid, or I have a square pyramid. I take the second one away, I have a shape of square planar. Guys, this is the chart I have describing electron clouds with electron geometry, very good. These last 2 slides, very, very good for determining it. As a matter of fact, I would definitely copy them and include them in your notes when you're taking the test. Is there any questions about what we're doing so far?
No.
What you have to do to determine molecular geometry, draw the Lewis structure, determine the amount of electron clouds around the center atom, From the number of electron clouds around the center atom, determine the electronic geometry. Then determine the molecular geometry by considering only the positions of the atoms. And that's basically what we're doing to do this. 2 domains. It's going to be linear. I've got 2 electron clouds. Both, in this instance, are bonding pairs. If I did have 1 lone pair here, would that change the shape?
No.
Because I've got 2 atoms, the shape is going to be linear anyway. That's the only instance where an electron pair, a lone pair on the center atom is not going to affect the shape. They want to push each other completely apart. We have a 180-degree angle. Only one shape, only one molecular geometry, that is going to be linear. I add a third one in there. I add a third electron cloud, trigonal planar. If all of them are bonding, I'm going to have an equal pushing apart. If I have an equal pushing apart, the bond angle is going to be 120 degrees. Now, say I have I have an iodine, which is really, really huge, and I have 2 fluorines. How's that going to affect the shape?
It'll be bent.
It's not going to be bent, Dylan, but if I have an iodine up here, it's going to push out more because it's a bigger ion. So the bond angle between the iodine and the fluorines is going to be greater than between the 2 fluorines. I take one of those atoms away. I now have a lone pair. I have a bent molecular shape. 3 clouds, 2 are bonding pairs, 1's a lone pair. They're getting pushed apart. They're getting pushed down by the third pair that's not seen. So if I have 3 domains, 1 lone pair, I have a bent molecule, no lone pairs, trigonal planar. Now, if I have a non-bonding pair and I have a bonding pair, the non-bonding pair is bigger than the bonding pair. So basically what happens is it pushes them down. So what this means to you is if I have something like tin fluoride, the geometry around the central atom is trigonal planar, the molecular shape is bent, and the bond angle between, if I go from the bond angle from the red to the blue to the red, that bond angle is less than 120 degrees because this electron lone pair is pushing it down to a greater extent.
Is the electron pair that's the lone pair, is it pushing it down because they aren't sharing electron?
It's got a bigger shape to it.
Okay.
I'm sorry. Let me go back to that one slide. This slide. It's not confined. You see, the bonding pair has to be between the 2 atoms. Okay? Dylan?
Yeah.
The bonding pair of electrons has to be between the 2 atoms. The lone pair does not have that constraint. So it can act larger, and as it acts larger, it pushes it down further. So
Okay.
that if I have methane with 4 hydrogens out here, the bond angles are equal. They're going to be equally 109.5. If I put ammonia in there, this lone pair pushes down to a greater degree than this hydrogen did. So with this pushing down to a greater degree, the bond angle between the H, N, and H is decreased to 107. I put a second lone pair in there. And that even decreases the angle further. We good?
Yeah, thank you.
Okay, I put 4 things around the center atom. 4 things, 4 clouds around the center atom. My electronic shape is going to be tetrahedron. If all 4 clouds are occupied by atoms, I have a tetrahedron molecular shape with a bond angle of 109.5, not the expected 90 degrees, because I can employ, I've got more than 4 things, I can employ the 3rd dimension. If I get a lone pair, my electronic geometry is tetrahedron. It's also my molecular shape. I have a lone pair there. My electronic shape is still tetrahedron, but my molecular shape is now trigonal pyramidal. So I get a trigonal pyramidal. This means I have 3 bonding, 1 lone pair. Again, bond angles are decreased because of the presence of the lone pair. I take another one of these off. What can you see, Joe? If I take another one of these atoms off of my molecule that has 3 atoms here, if I take one of these off and replace it with a lone pair, what am I going to see? What's the shape going to be?
What's it called? The triangle player or whatever?
No. What am I seeing? What am I seeing here? Take this away.
Oh, so 2, so bent.
Bent. It's going to look just like that. I still have 4 electronic domains, only 2 are bonding, 2 are lone pairs. And that bond angle is shrunk even more. Now, I have an electronic geometry of trigonal planar, 1 lone pair. I have an electronic geometry of tetrahedron, molecular geometry bent as well. Which one has the larger bond angle?
Right.
You agree with him, Dylan?
I'm not sure.
All right, let's think about it. This is trigonal planar. What did the bond angle start out to be?
$120.
Okay. This is tetrahedron. What did the bond angle start out to be?
One second, I'm trying to find it. $109.5.
Yes. So, first of all, they started off. The right one started off with a smaller bond angle than the left one. The other thing is, how many lone pairs are beating down on these 2 atoms? Right? The trigonal planar electron geometry only has 1 lone pair beating down on these two atoms. How many does this have?
Two.
So that's another reason why the bond angle is smaller for the tetrahedron bent shape as opposed to the trigonal planar bent shape. To summarize, if I've got 4 domains, I've got an electronic geometry of tetrahedron. No lone pairs, my molecular shape is going to be tetrahedron. If I have 1 lone pair, that turns this into a trigonal pyramid. 2 lone pairs, I have a bent molecule. The other thing about bond angles, if one of the bonds is a double bond, there's a greater electron density because look, we are dealing with 4 electrons between the C and the O, whereas we're only dealing with 2 between the Cl and the C. So this greater electron density pushes this bond down a little bit so that the bond between the Cl, C, and the O is greater than the Cl, C, and Cl. Do we need to work on this before I go into the larger and the non-octet ones? Are we pretty good with this so far? Do you want me to go through a couple of them?
I think I'm pretty good.
Joe? Okay, Joe. Can you draw me do this as well, Dylan. Draw me PCl3. Draw me a Lewis dot structure PCl3. Phosphorus has 5 valence electrons. Each chlorine has 7. So you have a total of 26.
Okay.
You got it, Joe?
Yep.
How many things are around the phosphorus?
There's 1 lone pair and 3 bonds.
So there's 4. What's the electronic shape?
What's it called? Triangle player, right?
Nope.
No,
That's
that'd be
3
the
things. That's 3 around it.
Oh,
I want
okay,
4.
I see now. It's tetrahydron, whatever.
Tetrahedron, okay? So I've got 4 things around. The electronic geometry is tetrahedron, okay? Now, what is the molecular shape of that?
Uh,
Tetrahedron? How many lone pairs do you have?
1.
So what is it?
It's a triangle pyramid.
Triangular pyramid. I would give you credit for that. Okay?
All right.
All right, I
Okay,
got
so-
about 10 minutes. I can get through the other two things. And then we are going to we're going to stop for the evening, and I'll review a little bit when we start up on Thursday. If I get 5 things around the center atom, the overall electronic shape is going to be trigonal bipyramid. If you kind of like want to think of it, you can see the 3 things at the bottom. They make a 3-sided pyramid on top, equally a 3-sided pyramid on the bottom. The bond angles in the equatorial, the ones on the plane, are 120 degrees. The ones that are on the axis are 180 degrees from one another, but 90 degrees away from the plane ones. So we have two distinct positions. We have the equatorial and we have the axial. Okay? Because of that, the equatorial get pulled off first. So if I'm doing this, if I'm taking something off of it, it's a lower energy for me to take one from the planar molecules than it is for me to take it away from the axial. Does that make sense to you? If it doesn't make sense, go with it. So if I take one of the atoms away and put a lone pair in there, the lone pair will push the other atoms away until you get this. It kind of looks like a lever right here. And where you have, I wish I could stop this twirling, but I can't. It looks like you have like a lever in the center and the two outer ones can go up and down. That's why it's called seesaw. Bottom line, if you have 5 clouds around your center atom, one's a lone pair, the molecular shape is going to be seesaw. Two things take away from the equatorial. If I take two things away, I'm going to have a T shape. And it's not exactly going to be a 90-degree angle because remember, I have lone pairs out here. It's going to push these towards each other a little bit. Same with this guy. These are going to be slightly pushed in a little bit. I think when I have one thing in here, so this angle is no longer 180. This lone pair pushes that down a little bit, and that pushes these a little bit closer. If I have 3 lone pairs, all 3 equatorials are gone. The only thing I'm seeing when I'm looking at the molecule itself is a straight line. So in summary, if I have 5 clouds around the center atom, trigonal bipyramid. No lone pairs, molecular shape's going to be trigonal bipyramid. 1 lone pair, seesaw. 2 lone pairs, T-shaped. 3 lone pairs, linear. So I'm going, basically, I'm taking one away. Trigonal bipyramid, going to seesaw, taking another one away, T-shaped, taking another one away, linear. Two more to do. 2 more to do and we'll be done with this. Octahedron. There are 6 things around the center atom. They repel each other equally. This means that the bond angles are going to be 90 degrees. If one is unshared, if it's a lone pair, then if you look at it, I've got 4 sides of triangles. I have a pyramid and it is the bottom of the pyramid is a square. So it's called a square pyramid. Now, if I take another lone pair away from that, I get a square planar molecule. The bond angles are 90 degrees from one another. So to summarize, 6 domains, electronic geometry octahedral, no lone pairs, molecular geometry octahedral. 1 lone pair, square pyramid, 2 lone pairs, square planar. Last thing I'm going to say, and then we're going to end this tonight. If you get asked a question, what's the shape of this? You look at your professor and say, beats the hell out of me. Which atom are you talking about? You have to understand when I have a larger, if I have a larger molecule, different shapes are going to compose that particular larger molecule. This carbon, 4 things around it. Electronic geometry is what, Dylan?
Tetrahedral.
Tetrahedral. Okay, it's tetrahedral. Do I have any lone pairs?
No.
What's the molecular shape?
Tetrahedral.
Okay, Joe. How many things are
Yes.
around this carbon?
4,
No. Double bonds, count 1.
3.
3. So what is the shape around this carbon?
Triangle planar.
Trigonoplanar. Okay.
There you go.
Are all of the things atoms that are attached to that carbon?
Yeah.
So the molecular shape is going to be trigonoplanar as well. Now, Joe, what about this last oxygen?
2.
So what's the molecular shape going to be?
Bent.
Bent. Absolutely. So that's how you would have to, if the professor doesn't give you an answer on that question, then the way you answer it is the shape around the left carbon is tetrahedron. The one around the center carbon is trigonoplanar, and the oxygen is bent. And that's the only way you can answer that question. Now, have you heard any reports about how they are doing this vaccine? How they study the vaccine and how they came up with it so quickly? They're actually doing computer models. They know from knowing what the DNA of the COVID virus is. They know what the shape of the COVID virus is. The way immunity works and the way antibodies work, it's kind of a lock and key system. So the antibody has to have the opposite shape of the virus. So it can lock onto it and then the body can get rid of it. So if they can figure out what the shape of the virus is, they have a damn good chance of making a vaccine that has the anti-shape of the virus. Therefore, they're able to get it out. Literally, when they were talking about the polio vaccine, it took them decades to get a polio vaccine. This, we're talking, they've got a vaccine that's almost ready to go out in less than a year. That's absolutely phenomenal, guys. And anyway, it's time. So I will see you on Thursday then. Hopefully we'll have a few more people, so I won't get to pick on you both so much.
All right. Have a good night.
Have a good night, Joe. You're okay with this? Does it make sense? Joe, Dylan?
Yeah. The only thing I missed was like copying that one page down, so I don't really know the angles, but
Yeah, just it's available. The slideshow is up and running on the course page, so you can get it
I'll
there.
have to go and see there. Yeah. All right.
Can I ask you a quick question?
Yeah, Dylan.
Will we be modeling any of the larger molecules on the test?
In other words, am I going to ask you what the shape is of this molecule?
Not
No.
the shape, but the Lewis structure.
No.
Okay, all right.
What
Thank you.
You're going to basically have one center atom. You're not going to have more than one center atom. Fair
Thanks
enough.
for making it easier.
I have to give you some kind of break.
All right. Have a good night.
You have a good night. Well, I'll see you later, won't I?
Oh, yeah. Yeah, you will.
In about 45.
All right.
All right. Take care. I will see you later.